Hello, my name is Edward Anderson. And today, what I am going to do is I'm going to teach the basics of operations management. Think of it as Operations Management 101 for the entrepreneur, what every entrepreneur needs to do. And by the end of this, you're going to understand what operations management is and why it's the key to success in the entrepreneurial world. We're going to talk to you about creating efficient operations management through well-designed processes. And to that end, we're going to teach you the language of processes, which is primarily visual and numeric. So we'll teach you how to map processes and how to measure how effective they are and analyze them for further improvement. So after this, you should be able to do the basics of effective process and operations management. Now, to begin with, let's talk about what operations management is. A lot of times we think of operations management as smokestacks. And indeed, manufacturing is a form of operations management. It's terribly important. Many entrepreneurs are actually going to be doing some manufacturing. That said, there are a whole lot of other aspects of operations management. For example, delivering hospital services, running emergency rooms, even delivering the mail. Those are all operations as well. And in an even different field further away, it's also about how you keep web servers up and functional so that they don't go down. So why is it important? First of all, as entrepreneurs, we all understand about the value proposition, what it is we're going to sell the customer that the customer is going to pay money for that we can make a profit off of. The thing is, if we do the value proposition and add in the customer demand, that's not enough. We also have to figure out how to get that value proposition to the customer. And this question mark, how we get value delivered to the customer, is what operations management is. Or in the startup world, oftentimes this is called value delivery. I would argue that without operations management, effective operations management, the best value proposition and the highest customer demand in the world is worthless, because you're not going to get any money until you actually deliver product to the customer. Until then, they're not going to start paying anything. So it's part of a tripod. There's the value proposition, there's creating consumer demand, and then there's delivering that value to the customer. Now, of those three, operations management is arguably the least intuitive. But the goal of this module that you're watching right now is to teach you the basics to survive. So, how do we do effective operations management? How do we survive and not shoot ourselves in the foot? Well, the first thing we have to understand are processes are the key to operations management. And a process is simply something that's done over and over and over again. Now, why does that matter? This is what I call the 5% problem. If you introduce your product and your research and development costs 5% more than expected, not great, but you can live with it. However, if your processes are ineffective, that 5% inefficiency is being realized day after day, month after month, delivery after delivery. And for many companies, 5% is the actual profit margin. And even if you're a really successful startup, say you get 20% margin, well, 5% of it, you're losing out 25%, a quarter of what you could be earning. It's a big deal. In addition to that, operations management, if it's done well, is a great deterrent to competitors, because decent operations management, good operations management, once you get it rolling, you get better at it, and it becomes much harder for your competition to duplicate. So having said all that, let's say what operations management really is. In my mind, it's the effective use of your business processes to deliver your value proposition to the customer and, wait for it, make money. So at this point, we're going to jump right in and talk about processes and how you manage them. The first thing is, you really can't do anything with a process until you understand what the process is. And effectively, that means you have to go out and draw it. You could use words to describe a process, but it typically isn't very, first of all, it's not very precise. It tends to lead to a lot of ambiguity, and it's really verbose. This is one of those things where a picture is indeed worth 1,000 words. So what I'm showing you is a process, and I'm also showing you the process flow diagram, which is sometimes just called the process map or the process diagram, or possibly the value map or the value process diagram, or some combination of those. Whatever it is a map, a diagram that shows you how the operation works and is the basis of all analysis of processes and improving your operations. If you can't draw it, you don't understand the process. So what I have here is a simplified doctor visit. And the process starts out with people who are arriving at the doctor's office, and that is this triangle here. And they're just waiting there. No values being added. But then you get to the check-in point. And at that point, you're working with a human being, and there is some value being added in the sense that the office knows who you are and will start getting things in motion. Now, at that point, you move to another waiting area, or at least a potential waiting area. And I want to be clear on this. If we have an operation where value add is occurring it's going to be a rectangle. That's how we draw it. So it's going to look like that. On the other hand, if there's some place where you wait, or even the possibility of waiting, then it's represented by a triangle, and it represents the fact that there is no value add occurring. After the customer has waited, after check-in, eventually they're going to get their history taken by a med tech. That's another operation. Values being added. It has to be done. And then there's another waiting period. Now, if this waiting period disappeared, there'd be no effect upon the value delivered to the customer. That's how you tell if people are in a process or could actually be manufactured goods too. They're just sitting there. That's how you can tell that it's a triangle, it's a delay. If you eliminate from the process, it makes no difference to the final product. At that point, you visit with the doctor. Now, two things happen here. One is you go to discharge after seeing the doctor. And while you're doing that, of course, there is the possibility for waiting again. The other thing that occurs is at the same time, as soon as you visit the doctor, and while you're getting discharged, your bill is being calculated because now you have the information from the doctor visit, but you don't have to wait on the discharge and the discharge instructions. However, before you go any further, going through this waiting area, you have to wait for both of these done. Otherwise, you can't go to paid checkout. You need a discharged patient, and indeed, then you can move to leaving, which is sometimes represented, even in services, called finished goods inventory. Which brings up a point. I've been talking about people in these processes and people waiting. It could be goods, like manufactured goods. A lot of times we just call them jobs. So it could be half-made widgets. The three classic waits are referred to as raw material inventory, work in progress inventory, or just WIP, and then finished goods inventory over here. Now, even when we're dealing with people, customers, we use the word WIP. The third component are flows, and that just means this is the way that patients or any other job are flowing through the process. And lastly, resources are the people and equipment that process the risks work. But unlike material, they don't actually move through the process and they're not used up. So to give you an example, let's just clean that up a little bit. When you visit the doctor, if it's important that you write down whom you're visiting, you would just write down doctor, or perhaps Dr. Al, if there's another doctor in the office. And at this point, you have a picture which can describe very quickly what the process is. And from there, we can go on and begin our calculations and analysis. So let's look at a simple process and begin to understand how to analyze it. So here's an example process, making Powerpuff dolls. For those of you who don't remember, this was a popular cartoon many years ago, about the time when my children were children. In any case, Powerpuff dolls do have to be assembled. And the process is as follows. We have a torso, and we have a pair of shoes, and they're connected by Alice. And then they're put into a whip where Bob picks them up and eventually attaches the head to that completed torso and shoes. That is completed, put into whip 2, from which Kathy picks up the completed doll, but then adds in a little green heart sign. And then when they're done, they put this in the finished goods inventory. Now, capacity for Alice, she can do 15 of those foot to torso connections a minute. Bob can do 10 jobs a minute at operation 2, and Kathy can do 12 jobs per minute at operation 3. Clarify, Alice, Bob, and Kathy are resources. And then op 1, op 2, and op 3 are operations. I'm going to simplify that diagram for the remainder of the presentation. And here it is. So let's go through some terminology and apply it to this process. First of all, this is perhaps the most important term that you need to understand, and that is capacity. And it's how much in jobs, customers, widgets, power puffs, etc., that can be produced in a specified period of time with no losses due to starvation, blockages, yield, downtime, etc. So what that means is, if my process isn't interrupted for any reason, there are no problems that occur. How many Powerpuff Girls can I churn out in an hour? That's what capacity is. It's the best you can do. In real life, of course, a lot of times you're not going to be able to do the best you can do. But in that case, that's not the capacity. Capacity is the absolute best that you can do. Now, capacity occurs at a number of levels. One is the operations capacity. So I just looked at one operation in isolation and ignores any constraints by anything else in the process or, frankly, anywhere else as well. And so if we look at this process, we'll find out that the capacity of operation 1 equals 15 jobs per minute. The jobs here being Powerpuff Girls. And for our purposes, I'm always going to use J to represent jobs and M to represent minutes. There are no meters in this discussion. Then let's look at operation 2. And operation 2 can complete their operation 10 times a minute. So they can process 10 jobs per minute. Operation 3 is 12 jobs per minute. Now, this is important. Why is it important? Because if you notice, operation 3 at most, given the way this process is drawn, is never going to see more than 10 jobs per minute arriving at the operation. And hence, at some level, the most that that operation can ever process is 10 jobs per minute because it's being starved by operation 2. But when we look at operation capacities, we don't care about that. What we want to know is if operation 3 were unfettered, they had whatever material they needed. WIP2 was just stocked tremendously high. How fast could they do things? So we now have our three capacities. Now, the next thing we want to know is what's the capacity of the process as a whole? Now, to find that out, we have to find out what the bottleneck is. And the bottleneck is that resource which constrains the capacity. It's what is strangling or constraining or holding back the process from doing anything better. In this case, it's clearly Bob. Bob, fortunately, only has to worry about one operation, and hence the bottleneck is going to be Bob, and that implies that Bob can actually complete 10 jobs per minute because he's just worried about operation 2, and hence the capacity of the process equals 10 jobs per minute. Now, this is really important because once we find the bottleneck, that is going to break the back of the problem of trying to understand not just what the capacity of the process and a lot of its other measurements, but also it's the first thing we need to know in order to do process improvement. Should we fire Bob? Well, the answer is no. And here's why. If you are an intelligent operations person and you understand that operation 2 is likely to be the bottleneck, you're going to employ your fastest worker there. So if you put Kathy there or Alice there and you're a good operations manager, you know that the process capacity is going to be even slower because Kathy and Alice just aren't quite as good at doing operation 2 as Bob is. Great. So that's one problem. We don't fire Bob. The second thing is, okay, we know the bottleneck is Bob. We want to increase capacity. Well, how do we do that? Well, what we can do is we can add Betty to help Bob out. Now, Betty is just as fast as Bob. She can also do 10 jobs per minute. So that's great. And what that means is, ultimately, is if we look from the point of perspective from Kathy, she's now getting 20 jobs per minute arriving to her. And so now she's no longer constrained. And she can produce at her capacity of 12 jobs per minute. Now, compare that for a moment. Kathy can produce 12 jobs per minute. Alice, because she's only responsible for op 1, she can produce 15 jobs per minute. So the bottleneck here is Kathy. And that implies that the capacity of the process now make that a little neater, is equal to 12 jobs per minute. Couple takeaways here. Number one, first off, always help out the bottleneck. If you sent Betty to help out Kathy, Bob, it wouldn't have done anything because Bob would have still been stuck producing 10 jobs per minute. And that would have choked off everybody else. Now, when Bob and Betty work together, their capacity now is 20 jobs per minute. So we just add them together. Okay. Now, at that point, the bottleneck may shift. And indeed, it did so here. So Bob and Betty, they're no longer bottlenecks. It shifts over to Kathy. And so we're at 12 jobs per minute. There is always going to be a bottleneck. Always. Now, another thing to note, which goes along with this, is adding Betty to help out Bob didn't double the capacity. It shifted the bottleneck, so it improved capacity, but it didn't double it. And that's commonly going to be the case. Another term that we need to know is cycle time. This is really just the inverse of capacity. So it's taking the capacity, instead of expressing it as jobs per minute or jobs per hour, it's saying, well, it's the number of minutes to do a job. How long does it take to complete a Power Puff Girl? And how often, that's at the operational level, at the process level, how often is it if we look at the end of the process and we see additional Power Puffs come off the end of the line? So it'd be Power Puff 1, and then there, a few minutes later, a few seconds later, there's going to be another Power Puff come off the line. And after that same interval, yet another one, and another one, and another one. And the cycle time would be that rhythm, the time between two completions of Power Puff Girls. It's just another way of looking at the capacity. Sometimes it's more useful. And also, frankly, when you start talking to people who do operations management for a living, honest to God, you ask them what a capacity is, and they may tell you that the capacity is 5 minutes per car. They won't tell you 12 cars per hour. They'll tell you 5 minutes per car. And so in practice, these are flipped. Now, why is that happen? Well, at the operation level, the time between, say, Power Puffs being completed, one Power Puff being completed, one Power Puff being completed, the third, and so on. That's how long that's exactly the same thing as how long that operation has to work on that Power Puff Girl. So it's a real easy way to conceive. In fact, when we do time and motion studies, it's a real easy way to conceive of capacity. Now, when you get up to the process level, that doesn't work anymore. The time it takes to go through an entire process from beginning to end, that's something else. Hang on. So when we look at the process, we're trying to express the inverse of the capacity. And the way to get at it is like, how long does it take the first Power Puff Girl to get off? What is the time to the second one, and the time to the third one, the time to the fourth and the fifth, and so on. And then we just take the average. All these metrics that we're looking at are long run averages. So occasionally some Powerpuff Girls are going to take a little longer than other because some Powerpuff Girls actually have braids on them and ponytails, but we're interested in the average. Okay. There's also a resource cycle time as well, but just hang on to that. We'll explain that later when we actually need it. So if we look at operation 1, well, the cycle time of operation 1, it's going to be the inverse of the capacity at 1. Okay, so this is definitional. And in this case, it'll be 1 over 15 jobs per minute. Okay, and you can actually say, hey, my cycle time is 1/15 of a minute per job. Now, that's kind of an ugly measure. It's legitimate, but I'm going to make things a little more convenient. So we're going to multiply it by 60 seconds per minute. And hence, that's going to result in 4 seconds per job. And if we do the same thing for operation 2, same thing's going on. It's 1 over 10 jobs per minute, which is equal to 6 seconds per job. And then cycle time 3, you go through and do the math, comes out to 5 seconds per job. Now, we can also find the bottleneck this way if we look at the cycle times. In this case, every operation has a resource. The resource don't share any operations, and hence, when we look at Bob, Alice, and Kathy, we notice that Bob has the longest cycle time associated with him. So again, the bottleneck is Bob because this process is never going to move faster in 6 seconds per job, and hence the cycle time of the process, which is always equal to the cycle time of the bottleneck, is, or Bob, is going to be equal to 6 seconds per job. So that's cycle time. In essence, really just another way to express capacity, but in practice, people use it all the time. So we have some other measures we need to look at. One of the most important is throughput. And the easiest way to describe throughput is to give you an example. So remember, the capacity of our Powerpuff process was 10 Powerpuffs, 10 jobs per minute. Now, the thing is, if there are only 8 jobs arriving per minute, then how many are actually going to leave the process? Well, there's capacity of 10, but 8 jobs are arriving, and ultimately those 8 jobs are going to be leaving per minute. What goes in must be what comes out. And so that output is going to be 8 jobs per minute. Now, that's not a capacity because it's not the best we could do. We are starving the process of the materials that it would like to use to get up to capacity. So we have to call that something else. And what it is called is throughput. In some ways, I wish they called it output because that's what it looks like to me. But the idea is that you're going through an entire process. You have all the operations done, then you leave. And hence the term throughput. So the thing to realize is this has a number of consequences. Number one, the throughput's never going to be higher than the capacity. So the throughput for this power puff process, remember capacity is 10 power puffs per minute, can be 8. The throughput could be. Throughput could be 6, it could be 5, it could even be 10, but it can never be 12. So throughput's always less than equal to capacity. Other fun facts that are important. It's going to be equal to the arrival rate as long as the throughput is indeed less than the capacity. Sometimes this is also flipped over, and in that case, it's called attack time. You'll run into that in some places, and some places they actually spell it TACT time. Companies that follow the Toyota production system, and there are a lot of them out there, tend to use takt time a lot. But it's really just a different way to express the throughput rate. Also, throughput excludes defects. So if there's 8 power puffs going through the process per minute, but only 7 of them do not have defects, or another way, one of them does have a defect, you're only going to count the 7 that does not have defects that are perfect. Now, this is a philosophical question, and actually you can get people arguing about it. I really don't have an opinion either way. Just make sure you know whether defects are included when people talk about throughput or they are not. Another measure we need to know is flow time. This is the time it takes one customer, widget, dozen cookies, whatever, power puff in our example, to get from the beginning of the process through all the operations to the end. Now, strictly speaking, you can talk about the flow time from point A to point B in a process, so it can be a portion of the process. And that works too, but you just got to make sure you specify, well, where is point A and where is point B? You also hear people talk about a rush order flow time, which is the time that would take somebody to get through a process if they didn't have to wait for anybody. So there's no downtime, there's no waiting in WIP, there's nothing. It's like going into a restaurant and you're a big star. You can go immediately to your table. There's no waiting. And by the way, probably not a lot of waiting for the waiters either, because they're going to be on top of you all the time. So that's what it's like. Easiest way to envision it is just to think, first job through the process, all the WIPs are empty. And then lastly, there's yield. And I was talking about the having 1 power puff defective of every 8. In that case, the yield would be 7/8. So that'd be 875, 87.5%. That's the number of jobs that go through a process without any defects the first time. So you're not going to count something as good for purposes of the yield if you have to push it back into the process to get it fixed.
Let's now calculate the flow time of our process.
So with what we know right now, we can only calculate the flow time when there's no waiting by the dolls. So we just look at these cycle times, which are a function of the capacities. And we know 4 seconds with op 1, 6 seconds with op 2, 5 seconds with op 3. What we'd like to know is, well, how long does it take to get through there if there is no waiting? Just imagine you're a Hollywood star. You're going into a restaurant. Everybody else is going to get out of your way. You don't have to wait whatsoever to get seated. You don't have to wait for the waiter to show up. You're the priority. Or another way, which also works, is think that you're the first job through in the morning and there's nobody there. In that case, we can talk about the rush order flow time. And the rush order flow time, in this case, we're spending 4 seconds with Alice. We don't have to wait for anybody, so there's no time spent in whip. Nothing in whip 2, then we spend 5 seconds with Kathy. So great. So in that case, the flow time for this rush order, and I'm even going to write down it's for a rush order, is equal to 4 plus 6 plus 5 equals 15 seconds total. Now, the thing is, that's really nice, but most of the time, there is waiting that's going to occur. And in general, if there is going to be waiting, it's usually in whips that occur before the bottleneck. So let's just argue that there's a wait of 10 seconds at whip 1, no wait here, and let's go through the process. In that case, for 10-second wait at whip 1, then the flow time is equal to the time at op 1, which is 4 seconds plus 10 seconds waiting in whip 1. We could get rid of it, but unfortunately, people are indeed waiting there. Plus 6 plus 0 plus 5, and hence we get 25 seconds. And for completeness, I'm going to do seconds up there as well. So this is common, by the way. Rush order for flow time, only 15 seconds here, but usually there's waiting, so it's going to take longer. And in fact, this 25 seconds is really an understatement. In manufacturing, the ratio of the flow time with waiting to the flow time without, oftentimes the factor of 8, 10 to 1, something like that. So it's huge. Better for services, but still not great. So a lot of people have trouble with separating cycle time and flow time. And it makes sense. Flow time is a rhythm. It's a time between completion of jobs. So, boom, cycle time. Boom, cycle time. Boom. Flow time is a duration from beginning to end. So I'm going to give you a couple of examples. I'll start with cars. I actually used to work in the automotive industry. And it turns out that almost all auto plants, no matter where they are in the world, who the maker is, what have you, they tend to produce a car every 60 seconds. Every 60 seconds, another car comes off the end of the line. And that's a rhythm. Every 60 seconds. Car 1, 60 seconds. Car 2, 60 seconds. Car 3. That is a cycle time. In comparison, to actually get through the assembly plant from beginning to end, that varies a lot, but typically it's on the order of 16 hours. By the way, one way you can tell the difference of a cycle time and a flow time for a process is a flow time is going to be longer, and often it's going to be much longer. Aircraft carriers. If an aircraft carrier, so I've been told by people in the Navy, is that they can launch 2 planes if everything is ready to go and everything's loaded up and there's no starvation, everything's just moving as fast as possible. In that case, they can usually get 2 planes off every 90 seconds. Hence, on average, every 45 seconds, there's another plane coming off the end of the carrier. So 45 seconds, plane. 45 seconds, next plane. 45 seconds, next plane, and so on. So in that case, the cycle time is equal to 45 seconds per launch. On the other hand, recovering a plane, refueling it, rearming it, sometimes getting the pilot out for a few minutes, sometimes even switching pilots, that can take all sorts of different time units, but it's not going to be 45 seconds. It's going to be 30 minutes on a good day. Okay. Again, flow time is much longer than cycle time. As a last example, we're going to talk about models. And when I mean models, I'm not talking about models of cars. I'm actually talking about fashion models on a runway. So if we're looking down on a runway, and we have 3 models, and I'm a big fan of Fabio's, honestly. And Giselle, I know, is a big deal still. And of course, Tyra Banks. So they're going to start at one end, and we'll call that point A. Customers are out here, by the way. And they start there. They start walking down the catwalk. They get to point B. That takes them 10 seconds. That takes them 10 seconds. And then at that point, they're going to go up. And it's going to take another 10 seconds to get to point C. So that's another 10 seconds. So, and this is crucial, is that when Fabio takes off at point A and makes his way down to point B, at that point, it's been 10 seconds to get there, but at that point, Giselle leaves immediately. So what's going to happen is Fabio, at the same time, he's making his way to point C. Giselle has made her way to point B. And again, at that point, Tyra starts off. So let's look at cycle time first. Cycle time is the minimum time between 2 jobs or in this case, people completing the process. And what's happening is, well, Fabio leaves the process. 10 seconds later, Giselle does, and 10 seconds later, Tyra does. So it's 10 seconds per person here. On the other hand, the flow time, it'll take Fabio 20 seconds to get from the beginning of the process, as will Tyra and Giselle and any other models. So hopefully that will lock that into your head. Let's look at a couple other measures. Utilization. It's the percentage of time you pay for a resource that the resource is actually working and not idle. So that means if you're paying a worker $10 per hour, he only has to work 8 minutes of that hour because there's not enough product coming his way. So 2 minutes of that, every 10 minutes he's idle. Then that means, well, his throughput is 8 per minute and his capacity is 10 per minute. 8 divided by 10, 80%. So that's how we get utilization. And what that means in some sense is for every dollar we pay that worker, 80% of that adds value, 10% of it's waste. We may as well be lighting it with a match. So one other thing I want to get to is work content. Now, work content is interesting because what it is for resource. You remember how we talked about sometimes they do more than one operation? Well, if they're doing more than one operation, their work content is to be the sum of all the cycle times that they have to spend on that operation, on those operations. So if they're doing 2 operations, you'd add up 2 cycle times and so on. And once you do that, the bottleneck can also be defined as that resource of the highest work content. And oh, by the way, on top of that, that bottleneck should be the busiest resource. If you schedule things right, it should be the busiest resource, and there should be nobody else who is as busy as the bottleneck. And then to get a resource capacity, we divide by 1 over the work content. Let me give you an example. We want to know each's resource utilization if jobs arrive at the beginning of the process at 5 jobs per minute. So we know that the throughput for the process is going to be 5 jobs per minute. Not a whole lot, but we know that's it. And by the way, that's also going to be the throughput for every resource. Because the process is starved. And in practice, most resources will be starved, maybe just a tiny bit. Even really good manufacturing processes tend to have utilizations like about 95, 96%. So they're starved a tiny little bit. Okay, so great. Now we need to know the utilization. Well, utilization of Alice is going to be the throughput she sees. So the throughput of Alice divided by the capacity of Alice. And in this case, throughput is 5 jobs per minute because she can't produce more than she actually sees coming to her. But she could do 15 jobs per minute. And what that means is she's got a utilization of 33.3%. Not good, not good at all. So, I mean, I'm sure we could imagine some cases where this would work out, but in general, 33%, terrible. That means you're burning 2/3 of your money. You're only getting 1/3 of each dollar that you pay else. We're going to do Bob next. And for Bob, his throughput is the same. It's five jobs per minute. But, and this is important, his capacity is 10 jobs per minute. And so his utilization is 50%. Not nearly as bad. Still bad, but it's not nearly as bad. And that's because he has less capacity. So at some level, every dollar we pay him, we get more useful work out of. And then just for completeness sake, I'll do Kathy, and she'll come out to be 5 jobs a minute over 12 jobs per minute. And that comes out to 41.7%. And this all makes sense because Kathy's utilization is much closer to Bob's, and that's because she has a lower capacity. So it's as it should be. So what would be interesting is, hey, what happens if each operation doesn't have its own resource anymore? So for example, what if Alice takes over Kathy's job? Well, in that case, we can tell that things are going to change, but how are they going to change? Well, for one thing, we need to really go after the work content, because adding these capacities doesn't make any sense, subtracting them doesn't make any sense, and so on. So let's grab the cycle times. Now, at this point, we can figure out work content, and from that, we can get the resource capacity. So work content of Alice, she's doing op 1. So it's a cycle time of 1 plus the cycle time of op 3, because she can't be doing op 3 at the same time she's doing op 1. She can't be doing op 3 for the Blossom Power Puff at the same time she's doing op 1 for the Bubbles Power Puff. And hence her work content is going to be 4 seconds per job plus 5 seconds per job. And that's equal to 9 seconds per job. So we know that. So we've got 9 seconds per job. And then at that point, we can get that capacity. And the capacity of Alice is going to be equal to 9 seconds. Excuse me. This is the resource capacity. It's going to be 1 over 9 seconds per job times 60 seconds per minute. So that capacity is going to be equal to 6.67 jobs per minute. And then Bob hasn't changed. He's still just doing operation 2. So his work content is still 6 seconds per job And that means his capacity is still going to be 10 jobs per minute. And oh, by the way, what that means is that Alice is the bottleneck. And moreover, not only is Alice the bottleneck, what that means is that the capacity of the process is equal to Alice's resource capacity, which is 6.67 jobs per minute. So what's happened is that by having Alice take over Operation 3 as well as Operation 1, now she's the bottleneck. Now, notice, however, that her operations, Op 1, Op 3, neither one was the bottleneck themselves. And in fact, we look at the cycle times, 4 seconds per job, 5 seconds per job. That's less than Operation 2, which is 6 seconds per job. But the thing is, Alice has got to do both Op 1 and Op 3, and we add them together, it's bigger than 6 seconds per job. And that is what drives us to the point where Alice is the bottleneck. This is why we always say resources are the bottleneck. And it's because they can be doing more than one operation. And particularly in services, this is very, very common. So let's take a look at utilization here. And the utilization for Alice is again equal to throughput at Alice over the capacity of Alice. And what that comes down to is 5 jobs per minute, because we're still at 5 jobs per minute for our arrival rate. And then, and I'll just put this down here so that we all know that 5 jobs per minute is still coming in. And then we divide that by Alice's resource capacity, which is 6.67 jobs a minute. And that's equal to 75%. And then if we look at Bob, well, nothing's changed for Bob. His work content didn't change. And so he's still at 50%. By the way, what this tells us, among other things, is since Alice isn't fully utilized, we really didn't need Kathy. So while we've lowered the capacity, the throughput's the same. And if that's the throughput we're going to constantly expect, getting rid of Kathy, replacing her with Alice was a good thing. So that's something we need to keep in mind. Last question. Flow times are really tough to get at. I told you before when we looked at this operation that there was a waiting time of 10 seconds at WIP 1. Most of the time, you're not going to know that. So if we wanted to find out the flow time for a job, and the number of the jobs are in the entire process are 30 and the throughput is 5 jobs per minute, actually, that's enough information. There is this thing called Little's Law, and it is wonderful. What it tells us, as long as we know the number of people inside a process, and usually it's a whole lot easier to count the number of people in a process. So there's 30 people here, or 30 jobs. A whole lot easier to count that than to actually measure their time that on average they go through the process. Even if you've got a good ERP system that's measuring that, I would double check by looking at the numbers and the throughput. So we've got 30 jobs in there, and we have 5 jobs per minute going in. doesn't stress capacity at all, and then 5 jobs per minute going out. And I can almost hear you asking me, say, ha, we're nowhere near 100% utilization. How can we have a waiting line? Well, turns out you can. And the reason is that if Bob's taking care of a customer and that customer, like, let's go into a cashier situation, customer has a whole mess of coupons and maybe uses a check, that customer is going to be very slow. And Bob's cycle time, when we talk about 10, it's an average, but it might be very long for that person. And the customer after that person is going to be held up. Now, the problem is the flip side isn't going to be true most of the time, which is if Bob's done with somebody really fast, that doesn't mean that the customers with Alice all of a sudden is going to accelerate. Now, it's going to take the same time as it always would. And so that's why you have lines building up. It has to do with the variability and the amount of time it takes to serve people. And it's also true for jobs and for manufacturing. Usually isn't as bad, but typically it's still there. And that's what drives these situations I was talking about earlier, where the minimum amount of flow time versus the average flow time, you factor 8-to-1. Pretty common. Okay. So how do we relate these? Well, the thing is, if we know the average line length, the average number of people inside a process, and by the way, this could also be the number of jobs in a process. It could be the number of partially completed cars in a process. Doesn't matter. In this case, we'll concentrate on Power Puff jobs. So we know how many Power Puffs are in that process, and we know the throughput. So we've got 2 parts of a triangle effectively. Once we have that, then what's going to happen is the flow time. It's really simple. We just take the number of jobs and divide by the throughput. It's very clean. And these are averages. So average flow time equals average number of jobs in the process divided by the average throughput. In fact, you'll find that realtors, if you ever talk to them, they kind of use this implicitly. You might ask them, okay, well, how many houses do you have in inventory? And they'll say, I kid you not, if you ask them, they might say 3 months of inventory. And you're thinking, well, inventory, that should be houses. Why are they saying months? What they're saying is they're implicitly using this law and saying, if I take my entire inventory and I sell at the rate that I've been doing so, I'll flush that inventory in
3 months.
That's what it means. So let's use this. Well, let's put down the formula here. Flow time equals L over throughput. Which equals 30 jobs over 5 jobs per minute. And if we crank that out, we're going to get 6 minutes. So it's going to take 6 minutes
to get from the beginning of the process all the way to the end.
Now, what's really cool about this, by the way, is I showed you this process diagram. We don't even need to know. We don't need to know what the structure is. It could be a blank page to us. It could be a black box. We don't need to know. All we need to know is that 5 jobs per minute is not exceeding capacity, and hence 5 jobs a minute are leaving, and the same relationship's going to hold. It's always going to be 6 minutes of flow time. So with that, we're finished up. I'm going to recap some of the important formulas you need to know. The bottleneck always has the highest work content in a process, or alternately, it has the lowest resource capacity. The process cycle time equals 1 over the process capacity equals the bottleneck's work content. Resource capacity equals 1 over the work content. Utilization equals throughput over capacity. Lastly, flow time, this is Little's law, flow time is equal to L divided by throughput. And with those 5 formulas, you can do all the analysis you need to do for most operations. And last point, when you're in a startup, you don't want to have complicated operations. Complicated operations tend to not be scalable, and they're not a good idea, given that you're likely to grow if things go well really quickly. And so, honestly, what I've shown you is enough for you to get started. If you get up to a situation where you're starting to get past the scaling game, you're starting to slow down, at that point, you better get somebody who knows what's going on in operations. With that, what we've done is we have explained to you what operations management is, so you should know how to use what operations management is. You should know why it's important for startups. You should also understand how the quality of your operations, the effectiveness, are determined by your business processes. And then we've taught you the tools so that you can better understand processes by drawing them out and then measuring them with very specific metrics, capacity, flow time, and so on. And then from that, doing some analysis from which you can determine at that point how you might want to improve the process. For example, to increase your capacity, you may want to add somebody to help out your bottleneck. So with that, I thank you.